This is a video from the Exam 2 Review Part 1. Let's take a look at Problem 8. Let W equal the set of all symmetric n by n matrices. Is W a subspace of the set of all n by n matrices? The answer is yes. So if I take the zero matrix for n by n matrices, that's equal to the transpose of the zero matrix for n by n matrices. And so the zero matrix belongs to W, and therefore W is non-empty. Okay, let A and B belong to W, and let K be a scalar. A scalar multiple of an n by n matrix is an n by n matrix, and the sum of two n by n matrices is an n by n matrix as well. So therefore, A plus B and Ka are n by n. All right, now, to show A plus B is symmetric, we need to show the transpose of A plus B is equal to A plus B. To show Ka is symmetric, we need to show the transpose of Ka is equal to Ka. Well, let's start with the transpose of A plus B. This is equal to A transpose plus B transpose. And this is the properties of the transpose. Right? Now, this is equal to A plus B, since A and B belong to W. And if A and B belong to W individually, they are symmetric matrices. And so, therefore, the transpose of A plus B is equal to A plus B. And that implies A plus B belongs to W. And W is closed under addition. When you want to show subspace, we show non-empty, and to show non-empty, we show the zero vector is in the set. And then we want to show close under addition, close under scalar multiplication. Now, if I take the transpose of Ka, this is K times A transpose. So essentially, I'm pulling the K out in front. But this is equal to Ka since A belongs to W. And so that implies the transpose of Ka is equal to Ka, and therefore Ka belongs to W, and W is closed under scalar multiplication. MULT period for short. And that's how we do problem number 8. Let's take a look at problem number 9. On problem number 9, I say let W equal the set of all n by n matrices A such that the transpose of A is equal to negative A. So is W a subspace of the set of all n by n matrices? The answer is yes. Now, first, if I take the zero matrix of size n by n, okay, and I take the transpose, absolutely, this is equal to the zero matrix for n by n matrices, right? And then this is equal to negative the zero matrix. And so that implies the zero matrix for n by n matrices belong to W. And W is non-empty. Just like that. Okay. Now, I'm going to let A and B belong to W and K be a scalar. Now, we have already established that A plus B and Ka are n by n matrices, right? Adding two matrices of the same size does not affect the size of the matrix, and a scalar multiple of an n by n matrix is an n by n matrix. So, now, we want to show the transpose of A plus B is equal to the opposite of A plus B. And the transpose of Ka is equal to the opposite of Ka. Okay. Now, how does that work? Well, let's start with the transpose of A plus B. This is equal to A transpose plus B transpose. But this is equal to negative A plus negative A. Negative A plus negative B, right? Why? Because A and B belong to W. So that has to be true. Now, this is equal to negative 1A plus negative 1B. Okay? But notice that negative 1 is common to both terms, and we are allowed to factor that negative 1 out in front. But this is the same as the opposite of A plus B. So therefore, the transpose of A plus B is equal to the opposite of A plus B. And so therefore, A plus B belongs to W. Now, let's take the transpose of Ka. This is K times the transpose of A. But this is K times negative A. Why? Because A belongs to W. I'm allowed to do that. Now, this one's a little tricky. I'm going to write this as K times negative 1A, like so. Okay? Now, if you don't mind, these scalars, here, maybe we'll do it this way, make it easier. So I could write this as K times negative 1A. Those are the properties of matrix arithmetic. But doesn't this equal to negative 1K times A? And can I shift the parentheses over to the KA? So this is negative 1 times KA, which is equal to the opposite of KA. And so, therefore, the transpose of KA is equal to the opposite of KA. And therefore, KA belongs to W. And so, therefore, W is a subspace of the set of all n by n matrices. I hope that makes sense. Okay. Now, I want to take a look at 11 to finish this off. So, if V1, here, we're going to do it this way. So, S is the set containing the vectors V1, V2, and V3. Okay? And V is the vector 2, negative 1, 3. V1 is the vector 1, 0, 0. V2 is the vector 2, 2, 0. And V3 is the vector 3, 3, 3. And I want the coordinates of V relative to S. And note that S is a basis for R3. That is absolutely a basis for R3. So, what do? So I'm going to set 2, negative 1, 3 equal to A times 1, 0, 0 plus B times 2, 2, 0 plus C times 3, 3, 3. If I set up my system, I get the following. I get A plus 2B plus 3C equals 2. And then I get 2B plus, right? 2B is here. And then 3C is here. Equal negative 1. And then I get 3C, that's here, equals 3. And so what that tells me is that C is 1. And then if I plug in, I get 2B plus 3 times 1 equals negative 1. 2B equals negative 4. B is negative 2. That's B. Now, A plus 2 times negative 2 plus 3 times 1 equals 2. So A minus 1 equals 2, A equals 3. And so, therefore, the coordinates of V relative to S are equal to the following. Now, A is 3. B is -2. And C is 1. And that'll do it for this video for the Exam 2 Review Part 1. And we did problems 8, 9, and 11. I did problem 10 on a different video. So, and that should do it for all of the, oh, not quite. So I have more to do. So we're almost done with the solutions for the first exam. I will go over more. So, okay, so this was 8, 9, and 11. Thank you.